Here's an interesting little preamp. This is a Proton AP-1000 stereo preamplifier. Just a little bit smaller and lighter than this guy, the 85-pound Parasound I've been working on. It has at least two issues that I'm aware of, and will also need some general service. The first issue has to deal with the tone control circuitry. The second has to deal with the headphone circuitry. So let's start by identifying the actual problem with the tone control circuitry. For tone control, we have your typical bass to adjust the low end, treble to adjust the high end, but we can also adjust the mid-range, and Proton calls this presence. We also have a tone bypass switch, so with this enabled, we just bypass the tone control circuitry altogether, giving you the raw signal. This can be very helpful for troubleshooting. The main issue with the tone control circuitry appears to be coming from the bass range, so something like 200 Hz and below. So on the scope, we're looking at a 100 Hz sine wave coming out of the preamp. The top is the left channel, bottom is the right. Right now I have the bass potentiometer at center position and the tone controls are defeated. You can see just how clean and symmetrical both channels are. But watch what happens when I enable the tone control circuitry. Wow. So not only was the left channel boosted significantly, but there's also a significant phase shift between the two channels. And when I adjust the bass potentiometer, we'll go to the full clockwise position. You get a little bit of boost or a little bit of adjustment from that left channel, absolutely nothing from the right. Now let's go to the full counterclockwise position. Once again, a little bit of adjustment from the left channel, nothing at all from the right. So what is going on here? I believe this odd issue is stemming from the bass potentiometer itself. And inside this one potentiometer package, there are actually two gangs, or basically two potentiometers, one for each channel. This is a 50K ohm potentiometer. Let's take some measurements of one of the gangs in circuit. Now you can read a resistance that's lower than your potentiometer if you have other resistors in parallel, but you should never read more. And look at that, we're at 3 meg, or 3 million ohms. Let's check the other side, from the center tap to the other outer tap. And here too, 3 million ohms. We should be reading 50,000 or less. So yes, there is absolutely a problem with this bass potentiometer. Let's remove it and take some more detailed measurements out of circuit. The bass potentiometer is a 774F T50KBX2. I don't have the datasheet for this, but I believe it was manufactured by Alps. The presence and treble potentiometers are identical, and of the three, this looks to be the only one that was cleaned with something at some point. Surprisingly, out of circuit, outer tap to outer tap for both potentiometers are reading completely open. So we can try and clean this and see if that helps, but because the outer taps themselves are not reading what they should, I don't have a lot of confidence that that will work. We may need to open this up, and a worst case scenario is just to replace it. Let's try cleaning it first. Cleaning did not seem to help at all, so let's open it up. Here's the potentiometer, or gang, of the right channel we've been measuring. And it should be pretty obvious as to why we have an open between the two outer pins. There's actually still perfect continuity across the entire length of the outer track, but take a look at the traces separating the pin from its side of the outer track. This one is almost completely gone, and this one is completely gone. This one I did clean with a cotton swab and some IPA, and it completely removed whatever was left there. So I'm not sure what happened, but both of these traces basically disintegrated over time. Let's measure the left channel's gang now. Measuring across the center and left taps, we actually get results that are close to what we'd expect. So we start at 42.6K, In the center, we're at 21.3K. And at the other end, we're at 80 ohms. So very, very close to what's expected. Let's measure between the center and right tap. This is open across the entire length of travel. And this makes perfect sense for the symptom we were seeing on the left channel, as we'll soon see when we take a look at the schematic. So unfortunately, there's no way I'm going to be able to repair this potentiometer, and these certainly aren't made anymore, so I'm going to see if I can find a suitable replacement. Here's what I was able to find. This is not an exact replacement, but it should work just fine. This is a Born's potentiometer, and compared to the original, there are two main differences. The first is the shaft length. This new one is 5 millimeters shorter. It should work just fine. There's still plenty of room for the knob to fit on the shaft. Second difference is the original was 50K, this is 100K. So this can cause issues, but we are able to compensate for this electrically. I'll show you that later, but first, let's get this installed and see if it resolves our main issue. The new potentiometer fits perfectly. There's no issue with adjusting the knob. So let's take a look at the output. I have all three tone controls set to the center position, and I have the tone control circuit enabled. Once again, we'll look at a 100 Hertz sine wave. And look at that. We no longer have the boost issue on our left channel, and we no longer have the phase shift issue from both channels. So now I'll adjust the actual base potentiometer. We'll go to the full counterclockwise position. This should cut it. And it does. And now we'll go to the full clockwise position. This should boost it. And it does. And they look great. So that's what it was, the potentiometer. Let's take a look at the schematic and see why that caused this issue. Here's the relevant portion of the schematic. This is an active tone control circuit, more specifically a Baxandall tone control circuit. The Baxandall circuit and its many variations have been around for decades. There are essentially two sections to the circuit. We have the actual tone control, which is on the left. This is where you're adjusting your potentiometers by frequency range. Here's bass, presence, and treble. The other section is an amplifier, which is over here on the right, this entire section. These two work together to affect the cut or boost of a signal by frequency range according to the position of the potentiometer before being sent out to the preamp outputs. Now this is definitely more complicated than what we need for this discussion, so let's simplify it. On this drawing, I've removed the presence and treble sections completely, and I've replaced the discrete components in the amplifier section with this symbol. Our signal enters from the left, travels through a fixed 12K ohm resistor, and then 1/2 of our base potentiometer, so 0 to 50K. Before entering the amplifier. From the output of the amplifier, we feed back some of the signal, again through a fixed 12K ohm resistor, and the other half of our base pot, 0 to 50K, before being fed back into the amplifier. The gain of this circuit is simply the ratio of the feedback resistance to the input resistance. So these two values combined to these two values combined. With the potentiometer at mid position, these two values are equal to these two values. You have a ratio of 1, which gives you a gain of 1. Whatever's at your input will be at your output. As you rotate the pot clockwise, these two values will increase relative to these two values. The ratio is greater than 1. This produces boost. As you rotate the pot counterclockwise, these two values will be greater than these two values. That gives you a ratio less than 1, which produces cut. With this information in mind, let's recall the measurements we took from that left channel's potentiometer. The left side, or the input signal side, was measuring pretty normal, somewhere between 0 and 50K. The right side, however, or the feedback side, was measuring open. And the circuit is essentially going to see this as an extremely high resistance. So that means no matter where we adjust the base potentiometer, this right side, or feedback side, is always going to dominate. That means the ratio is always going to be greater than 1, which is always going to produce boost. When changing the resistance of a pot in a circuit like this, so in our case from 50K to 100K, the result is a change in sensitivity. Now in more extreme cases, In more extreme value changes, you can consider compensating by replacing the value of these two resistors here. If the potentiometer resistance increases, you'll want to increase these values as well, and vice versa. In our case, the impact was relatively insignificant, and so no compensation is needed. One problem down. Let's take a look at the topic for the next video, the issue with the headphone circuit. A missing channel. Stay tuned. Thanks for watching.